49 satellites fell out of the sky in a single day. Not because of a malfunction, not because of human error, because the sun, the same star you glanced at this morning, without a second thought, exhaled. That's it. One breath. One invisible shockwave rippling outward at millions of miles per hour. And 49 pieces of cutting-edge technology, each worth millions of dollars, each carrying the dreams of a tech billionaire, tumbled silently back into Earth's atmosphere and burned. Now imagine if that breath had been deeper. In 2023, a solar event equivalent to 1 billion hydrogen bombs detonating simultaneously sent a shockwave crashing into North America. Communications went dark. Entire regions blacked out. And here's the thing that should terrify you, that wasn't even close to the worst the sun can do. So when NASA pointed its most advanced space telescope directly at the surface of the sun and captured images no human had ever seen before, images so detailed, so raw, so wrong-looking, scientists didn't celebrate. They went quiet. What they saw on those images was rain, fire, grass, cracks the size of countries, and something moving beneath the surface that should not be moving at all. But to understand what NASA found and why it changes everything we thought we knew about the star we orbit, we have to start at the beginning. Not with the images, with the decision to look in the first place. Here is something that sounds like a riddle. The most important object in our solar system is also the least understood. We've sent rovers to Mars. We've touched the rings of Saturn. We've flung a probe beyond the edge of our solar system entirely. But the sun, 93 million miles away, the engine of all life on Earth, has been, until very recently, a mystery hiding in plain sight. Part of the reason is obvious. You cannot look directly at the sun. That rule applies to your eyes, and it applies in a surprisingly similar way to our telescope. The sheer heat and radiation pouring off its surface overwhelms most instruments. Getting a clear picture of the sun is like trying to photograph a light bulb from the inside. But there's a deeper reason scientists have been studying the sun with increasing urgency, and it has nothing to do with scientific curiosity. The sun is getting louder. Not in sound space is silent, but in activity. Solar flares, those massive eruptions of charged plasma that shoot off the sun's surface, have been increasing in frequency and intensity. And every time one of those flares lines up with Earth, the consequences are real and immediate. In 1989, a solar storm knocked out power across an entire Canadian province for 9 hours. In 2003, flares disrupted airline communications across polar routes. And historically, records going as far back as 1580 show at least 33 significant solar events that caused measurable damage to Earth's technology and infrastructure. The grandfather of them all, the Carrington event of 1859, was so powerful that telegraph machines caught fire. Operators received electric shocks. The aurora borealis was visible as far south as Cuba. If a Carrington-level event hit Earth today, with our global dependence on satellites, power grids, and digital communication, the estimated economic damage would be measured in trillions. This is the world NASA was navigating when it launched the Solar Dynamics Observatory STU in 2010. This wasn't a mission of curiosity. This was reconnaissance. Scientists needed to understand the sun the way a general needs to understand an enemy, in detail, in real time, and with enough warning to react. STO entered a geosynchronous orbit above Earth, locked its instruments on the sun, and began transmitting data back to Earth at a speed that made its predecessors look prehistoric. Where earlier solar satellites took 12 minutes to send a single image, STO sent one every 0.75 seconds. The picture quality was 10 times sharper than anything that came before. And then it started looking, layer by layer, like peeling back the skin of something alive. What it found beneath that skin would rewrite textbooks. The sun has layers. Most people know this the way they know the capitals of countries they've never visited, vaguely, theoretically, without emotional weight. But understanding those layers is critical to understanding what NASA found. Quickly, the outermost layer is called the corona, a shimmering halo of superheated plasma that extends millions of miles into space. Below that sits the chromosphere, a turbulent middle layer, and at the bottom, the layer we see when we look at the sun during sunset, is the photosphere, the actual visible surface, burning at around 5,000 degrees Celsius. Each layer operates at a different temperature, and because different temperatures emit different wavelengths of light, studying each layer requires switching to a different lens, a different slice of the electromagnetic spectrum. NASA's STU was built to do exactly this. It carries instruments that can photograph the sun in multiple wavelengths simultaneously, essentially giving scientists X-ray vision for a star. They started at the top, the corona. When the images came in at the ultraviolet wavelength tuned to the corona's temperature, scientists leaned forward in their chairs, because what they saw made no sense. It was raining on the sun. Not water, not ice. Plasma superheated rivers of charged particles was falling downward from the corona toward the sun's surface in long glowing streams, cascading, pouring like a slow-motion waterfall made of liquid fire. The question that immediately followed, why? Here is what happens when you follow the science far enough. The sun is threaded through with magnetic field lines, invisible rivers of force that run through its plasma like wires through a wall. When that plasma, the soup of charged particles that makes up the sun's body, comes into contact with these magnetic fields, something violent happens. The magnetic field grabs it, flings it upward, accelerates it outward in a burst of energy so immense that a single solar flare can release the equivalent of billions of nuclear bombs detonating simultaneously. These flares shoot out from the sun's surface at millions of miles per hour. They are, in every meaningful sense, catastrophic events. Yet, they have a ceiling. As they travel outward into the corona, moving away from the sun's core, they lose energy. They cool. The same plasma that was ejected at terrifying velocity begins to slow, begins to condense, and then, pulled back by the sun's gravity, it falls. It rains. Scientists gave this phenomenon a name, coronal rain, and while the name sounds almost gentle, the scale is anything but. The plasma streams scientists watched falling on the sun's surface were moving at speeds that would take them from Earth to the moon in minutes. The raindrops were structures larger than cities. But here's what made coronal rain more than just a spectacular visual. It is directly connected to solar flares. Every eruption that punches off the sun's surface eventually collapses back. The rain you see is the aftermath of the explosion. And understanding that cycle, understanding where the plasma goes, how fast it returns, what it does when it lands, is critical to predicting when the next flare will hit. Which means those falling rivers of fire, they were clues. But that was only the first layer. NASA still had 2 more to peel back, and what was waiting in the chromosphere would be stranger still. Drop the wavelength, tune the instruments lower, to the cooler signature of the chromosphere. Let the new images load. And there, spread across the middle layer of the sun, was something that looked like there is no other word for it: grass. Thousands upon thousands of thin, sharp, needle-like structures, each one jutting upward from the chromosphere like a spike. They appeared suddenly. They grew. And then, at speed scientists had to double-check because the numbers seemed wrong. They were launched fired outward into the corona like projectiles. Their speed, approximately 60 times the speed of sound on Earth. Their height, taller than Mount Everest. Many were taller than several Mount Everests stacked, and they were appearing and disappearing in cycles of roughly 5 minutes, like the sun was breathing inhaling spikes, exhaling them, inhaling, exhaling. Scientists called them spicules. The mechanism behind them is one of the most elegant and slightly terrifying things happening on our star's surface. Here's the root of it. The sun does not rotate as a solid object. Its equator spins faster than its poles. Think about what that means for a moment. The surface of the sun near the middle is lapping the surface near the top and bottom, completing a full rotation days faster. This differential spin, this constant mismatch in speed, does something brutal to the sun's magnetic field lines. It twists them. Imagine winding a rubber band around your fingers, tighter and tighter, until it begins to knot and loop and tangle. That is what the sun's differential rotation does to its own magnetic field, constantly wringing it, coiling it, until the field lines snap against each other and release their tension in bursts of energy. Those energy bursts create shock waves in the chromosphere. And those shock waves do to the plasma what a speaker does to water placed on its surface. They make it jump, violently, repeatedly, in sharp, pointed columns that race upward at supersonic speeds. But here's where coronal rain and spicules connect in a way that took scientists years to understand. Those spicules shooting upward into the corona are carrying plasma with them. They are the delivery mechanism. The sun's magnetic convulsions are pumping hot material up into the corona, where it eventually cools and falls back as coronal rain. The sun has a circulation system, a heartbeat made of plasma and magnetism. Now there was one layer left, the deepest one, the one we see every morning. Here is something that should rewire the way you see the sunrise tomorrow. That smooth orange disk you see at dawn, the clean, featureless glow of the morning sun, is a lie. Or rather, it is a limit of what the human eye can resolve at 93 million miles of distance. Because when NASA's Stu turned its instruments to the photosphere and captured images at visible wavelengths, the layer we look at every single day, the surface of the sun, looked nothing like a surface. It looked like something boiling, covered edge to edge in structures scientists initially thought were image artifacts. Pixels, noise in the data. They zoomed in to clean the image up and realized they were looking at cells, thousands of them, enormous, irregular hexagonal structures covering every inch of the photosphere, each one a churning column of plasma rising from below. They called them solar granules. Now the word granule calls to mind something small, a grain of sand, a sugar crystal. So understand this clearly. Each solar granule, each one of these small structures on the sun's surface, is roughly the size of the state of Texas. They form because of a process identical in principle to what happens inside a pot of boiling water or inside the Earth itself. The plasma near the sun's core is intensely hot. Hot plasma rises. It reaches the surface, spreads outward, cools slightly at the edges, and then sinks back down. From above, looking down at this circulation pattern, what you see are the tops of the rising columns' bright centers with darker lines between them where the cooled plasma is descending. Those dark lines between the granules, that's what NASA's camera captured as cracks in the surface. The sun is not cracking, it is digesting, constantly cycling plasma from its core to its surface and back in a process that never stops, never slows, and has been running for 4.6 billion years. But the granules were not the only thing scientists noticed in the photosphere images. There were spots, dark, irregular, scattered across the surface like bruises. And this is where the story takes a turn, because those spots are old news. We've known about sunspots for centuries. Galileo drew them in the 1600s. But what Stu's detailed images revealed about why they form was new, and it was disturbing in a way that connected every piece of what came before. Remember the twisted magnetic field lines, the ones causing spicules in the chromosphere? When those tangled loops of magnetic force penetrate into the photosphere, they create localized zones where the magnetic field is so strong it physically inhibits the plasma. Imagine iron filings near a magnet. They don't scatter freely, they lock into alignment with the field. Same thing happens to plasma particles in these high magnetic zones. They align, they stop vibrating against each other as freely. And when plasma stops vibrating freely, it cools. When it cools, it darkens. Sunspot. The same magnetic convulsions causing rain in the corona and spikes in the chromosphere are leaving bruises on the photosphere. Three completely different phenomena in three completely different layers, all caused by the same underlying force. The sun's own magnetic field, twisted against itself by its own differential rotation, is simultaneously raining fire, growing mountains, and scarring its own face. It is a system, a chaotic, interconnected, living system. And here's the twist that changes everything. That system is accelerating. There is a question buried in the original mission that NASA hasn't fully answered publicly. If we've been studying the sun since the 1990s, if we already had SOHO and stereo and decades of solar observation data, why did so many space agencies around the world simultaneously decide within the last decade to dramatically increase the number of missions aimed at the sun? 10 solar missions in 20 years, from agencies that don't always agree on anything. The official answer is data resolution. STO takes pictures 10 times sharper than its predecessors. More missions mean more data from more angles. The more you look, the more you understand. That answer is true. It is also, perhaps, incomplete. Because buried in the data from these missions is a pattern that solar scientists have been tracking with growing unease. The sun's activity cycles are becoming harder to predict. The sun operates on an approximately 11-year cycle of activity solar minimum, where sunspots are rare and flares are infrequent, and solar maximum, where the surface churns with activity and Earth faces increased risk of disruption. Scientists have known about this cycle for over a century, but recent cycles have behaved unexpectedly. Solar cycle 24, which ran from 2008 to 2019, was the weakest in a century. Scientists predicted solar cycle 25, the one we're currently in, would be similarly quiet. They were wrong. Solar cycle 25 has been dramatically more active than predicted. More sunspots, more flares, more coronal mass ejections, those massive clouds of magnetized plasma that, when aimed at Earth, can disable satellites, corrupt power grids, and knock out communication networks for days or weeks. In May 2024, the most powerful geomagnetic storm in 2 decades struck Earth. Auroras were visible as far south as Florida and Texas. Some farmers reported GPS-guided agricultural equipment going haywire midfield. It was beautiful. It was also a warning. STO and its sibling missions are not just scientific endeavors. They are, in a very real sense, an early warning system. Every image transmitted back to Earth is being scanned, processed, and analyzed for signs of the next major eruption. The goal is to reach a point where scientists can predict a dangerous solar event days or weeks in advance, enough time to power down sensitive satellites, warn airline crews on polar routes, and prepare power companies to protect their grids. We are not there yet, but we are closer than we have ever been. And the images from STO, the rain, the grass, the boiling cells, the bruised spots are the raw material from which that prediction capability is being built. Every phenomenon NASA revealed in those images is a variable in an equation scientists are still solving, and the stakes of solving it correctly are civilizational. In September 2023, something remarkable happened that received far less global attention than it deserved. India launched a satellite called Aditya L1. Named for the Sanskrit word for sun, it was ISRO's first dedicated solar observatory, and its destination was not an orbit around Earth, or even a simple trajectory toward the sun. It was aimed at a specific invisible point in space called Lagrange point 1 L1. To understand why this matters, you need to understand what a Lagrange point is. Between any two massive bodies in space, in this case, the Sun and Earth, there are 5 positions where the gravitational poles of both objects balance out precisely. An object placed at these points doesn't drift toward one body or the other. It just stays, suspended in equilibrium, orbiting the Sun in perfect lockstep with Earth. L1, the point directly between Earth and the Sun, is 1.5 million kilometers from our planet. It is, in practical terms, the perfect observation post. A satellite stationed at L1 gets an unobstructed view of the Sun at all times. No eclipses, no shadow, no interruption. It sees whatever the Sun does in real time before Earth does. Placing a spacecraft at L1 and keeping it there is an exercise in surgical orbital mechanics. ISRO had never done it before. The spacecraft must arrive at L1 with precisely the right velocity, fast enough not to fall back toward Earth, slow enough not to overshoot toward the Sun, and with exactly the right angle to slip into a halo orbit around the point, rather than shooting past it. After a 127-day journey, Aditya L1 arrived. It inserted itself into a halo orbit around L1 on January 6, 2024. India became only the fourth entity in history after the US, Europe, and China to successfully operate a solar observatory at L1. And then it opened its eyes. Aditya L1 carries 7 scientific instruments. They study the Sun's corona, its magnetic field, solar wind particles, and X-ray flares. Some of its instruments are designed to measure phenomena that STO, despite all its capabilities, cannot see from Earth's orbit because Earth's own magnetic field and atmosphere filter out certain types of solar radiation before it reaches us. From L1, nothing is filtered. Everything arrives raw. The data Aditya L1 is now sending back, combined with STO's images, combined with ESA's solar orbiter mission, which is actually flying closer to the Sun than Mercury's orbit, combined with NASA's Parker Solar Probe, which has physically flown through the Sun's corona, is building the most detailed, multi-angle, multi-wavelength portrait of our star ever assembled. And here's the thing that keeps solar physicists both excited and slightly up at night. The more detailed the portrait becomes, the more the Sun reveals things we didn't expect to find. The coronal heating problem, why the corona is millions of degrees hotter than the surface directly below it, which should be physically impossible, remains unsolved. The exact mechanism that triggers a solar flare's explosive release of energy is still not fully understood, and the Sun's magnetic field, which drives every phenomenon we've discussed, is generated by processes deep in the Sun's interior that we can only infer, never directly observe. We have the most advanced solar observation network in history. We can photograph the Sun's surface down to features the size of cities. We can measure the sound waves bouncing through its interior like a seismograph measuring earthquakes. And still, the Sun keeps secrets. So let's land the plane. What NASA's Solar Dynamics Observatory revealed, and what a growing constellation of international solar missions is continuing to map, is that the Sun is not a simple object. It is not a ball of fire burning steadily in the void. It is a dynamic, layered, magnetically driven system of interconnected phenomena, each one feeding into the others, each one sending ripples outward that can, and do, reach Earth. The coronal rain scientists watched falling on the Sun's surface is the aftermath of the same magnetic explosions that send solar flares hurtling toward Earth. The spicules, those Everest-high spikes, firing into the corona at 60 times the speed of sound, are the Sun's own circulation system at work, pumping plasma through its layers. The solar granules boiling across the photosphere are convection on a scale so vast that a single cell would swallow the United States. And the sunspots, those bruised, cooled patches that have fascinated humans since Galileo, are the fingerprints of the same twisted magnetic field causing all of it. One force, one system, playing out simultaneously across 3 layers of a star 1.3 million times the volume of our planet. We watch it because we have to, because 33 times in recorded history that system has reached out and hurt us. because 49 satellites fell from the sky in a single day, because a billion hydrogen bomb pulse blacked out North American communications in 2023, because the Carrington event, the biggest solar storm in modern recorded history, happened once, and it can happen again, and next time, we will not be sending telegrams. We will be running hospitals, flying planes, keeping patients alive on machines that need power to run. The new missions, Aditya L1, Parker Solar Probe, Solar Orbiter, are buying us time. Every image is a clue. Every instrument reading narrows the uncertainty. Every successful prediction of a solar event is a rehearsal for the day we really need to get it right. But standing in the control rooms of these missions, watching data stream in from a star 93 million miles away, scientists will tell you something that doesn't make the press releases. The more we learn, the more we realize we don't know. The sun has been burning for 4.6 billion years. It will burn for roughly 5 billion more. In all that time, it has not once repeated exactly the same pattern twice. Its magnetic field is never quite the same shape. Its flares are never quite the same strength. Its cycles are predictable enough to see in hindsight, and just unpredictable enough to surprise us in the moment. Every morning, you see it rise, smooth and orange and distant. But now you know that surface is boiling. Texas-sized bubbles rising and falling in an endless circulation. Mountains taller than Everest shooting upward and collapsing in 5-minute cycles. Magnetic loops twisting through the plasma, cooling dark spots into the face of the sun like bruises. And somewhere in those layers, right now at this very moment, something is building. A flare is coiling. A knot in the magnetic field is winding tighter. The plasma is rising, and the field is twisting, and the storm is gathering. We just don't know yet when it will let go.